Our next speaker is Christophe Andrieu, and he needs no introduction, actually. So, well, yes, he's a professor at statistics at Bristol. He's been there for a very long time, and I'm sure many of you know, at least read Christophe's papers at some point in your life. And today he's going to give this very interesting talk about using integrator snippets or ODEs in Monte Carlo. Okay. Yes, Christophe, the floor is yours.
Okay, thank you very much for the nice introduction. And so you were pleased that basically you didn't need any introduction today. It was the first time, and I'm happy that I still don't need any introduction. It may change in a few years' time. Okay, so this is joint work with Chang Wang, who is back in China now, and Mauro, who finished his PhD this year and is looking for a job. So if you know of any opportunity, he'd be interested. So again, relating to what, in relation to the previous talk, I was glad that Francesca spoke this afternoon, because I'm not the only outlier this afternoon. So you would see that what I'm going to talk about is quite different from what you're familiar with, but the mathematical tools are very much related to the things you've heard about throughout the week. And don't hesitate to stop me if something is unclear, because I may have assumed things that are standard in my sort of community and may not be obvious to you. Okay, so that's the plan. And I'm going to go a lot through some background. So for you, that would be easy background, trivial background, but not maybe for others. So I've tried to cater for basically the people who really are not familiar with sequential Monte Carlo methods in particular. So that may be a bit boring for some of you. So what are the key messages if you fall asleep at some point? This is what you should remember, that basically we developed some novel sequential Monte Carlo methods, or sequential Monte Carlo methods. I'll try to explain what they are, but they are Monte Carlo methods that work in a very specific way. And what we try to do in this work is to show how to, in a way, optimally, and of course we don't prove any optimality, but how do we use deterministic flows, that is solutions of ODEs, in order to explore the support of the target distribution we are interested in sampling from. So that's the key idea. And one king or queen application in our work is, of course, hybrid Monte Carlo, and not because we believe that it's a good method, but because it's a very, very popular method. But in fact, there are other scenarios where this may be interesting, and I won't expand too much on that, but I'll show you some picture that will be very suggestive of the sort of things we've got in mind. Okay. And in particular, the sorts of things we would be interested in is in scenarios where some of the geometric properties of the distributions you're trying to sample from can be described through ODEs, right? And as I said earlier, one of the key aims of this work was try to basically avoid as much computational weight as possible while using these things. And you'll see exactly why, what I mean. And the method seems to work extremely well, and I'll show you some results that are not in the current technical report, where we show that actually the algorithm is extremely robust to bad calibration of the parameters of the algorithm. That is, the algorithm can be made to be adaptive and recover from bad calibration. And that's, in my view, quite remarkable. Okay, so some background on sequential Monte Carlo samplers. So what are sequential Monte Carlo samplers? So the first thing is that you're interested in sampling from some distribution mu that is distributed on, that is defined on some space Z. And I won't assume too much about that distribution. So what is the main idea of sequential Monte Carlo sampler? So it's a bit in the name, right? So what you're going to do is that instead of trying to sample from mu directly, what you're going to do is define a sequence of problems that are easy to difficult to sample from, where difficult is sampling from mu. And in order to do that, you're going to define a sequence of distributions on the same space Z, okay? So indexed by n, that goes from 0 to p. And what we're going to impose is that the endpoint of the sequence is the distribution you're interested in, and mu naught is typically a distribution that you can sample from directly. It doesn't have to be the case, but it's an easy to sample from distribution. And then the other distributions, somehow they interpolate, okay, between quotes, between the simple to sample distribution to the complicated distribution you're interested in, right? And then comes in the, so that's the sequential, if you like, and now is the Monte Carlo bit. So how do we implement these algorithms? The idea is that basically you're going to consider a cloud of samples, right? For each time instance, okay, or iteration. And there are capital N of these samples. So that's a cloud of points whose distributions and concentration in the various regions of the space is going to represent mu n at each time n. And what we are going to do is to use, so this sample, imagine that it approximates mu n at time n. What we are going to try to do is to propagate this cloud of sample in such a way that at the next iteration, that cloud of point is going to represent mu n plus 1. So that's the idea of sequential Monte Carlo methods. And the way that works, and I'll provide some details earlier, it works using basically a kind of important sampling resampling mechanism, right? Okay, so just a toy example, right? So imagine that you're interested in a Bayesian problem where you've got, say, a prior distribution mu naught, okay? And you've got a likelihood function with n data points, right? And for some reason, you believe that basically incorporating the data sequentially is going to make your problem easier, okay? That is basically you assume that having all the data is going to be such that the concentration of Z on some points is going to make sampling too difficult. So what you do is that you introduce the data sequentially. So here you see that you would, to define mu n, basically you would only consider the first n data points, okay? So that's just to fix ideas. And for those of you who have heard about particle filters, sequential Monte Carlo samplers are very much related to particle filters, but they differ in, you know, in some certain ways that are not too important here. So a bit more details about the mechanism that allows one to propagate the cloud of samples. So let's assume that we've got samples at time n-1 that represent mu n-1, okay? And by representing, what I mean is that I approximate expectations with respect to mu n-1 with those samples. That's what representing means here. Okay, so the way we are going to move from samples that represent mu n-1 to samples that represent mu n is first by mutating the samples at time n-1. So basically, we've got a mutation Markov kernel, typically, that is going to be centered at each of the particles for simplicity. And basically, you sample a Zn tilde, okay, from this kernel distribution. And of course, there is no reason for this Zn tilde to be distributed according to mu n, right? I haven't said much about Mn. So what we are going to do, and I provide some more details, is that in fact, what we are going to do, because Zn tilde is not distributed according to mu n, we are going to do important sampling, but we are going to do important sampling on the joint space of Zn-1 and Zn tilde, okay? So this is an importance weight. And you see that in order to define the importance weight, so we've got, this is what we've sampled from, right? So we had samples from this distribution. We've sampled mutation kernel. And of course, because we are on the joint space, we've got to complete the distribution we are interested in, which is mu n, with a so-called backward kernel. Okay, it's just to make sure that we've defined an importance weight on the joint space of z times z. Okay, and then n-1 is user defined. And once you've got these weights, for reasons that I will not explain here, basically there's a selection step. That is, you use these weights, which give importance to various values of Zn tilde. You use those weights in order to perform selection. And basically what you say is that my samples at time n that are going to represent mu n are going to be basically a resampling version of the Zn tildes, of the mutated samples. And the way you do it is that you use these importance weights, right? So about that backward kernel, we are going to get rid of it, okay? But what I'm going to tell you here is that basically by getting rid of it, basically we are going to impose some structure on Mn, okay? So this is just a repeat of what I said earlier, that basically we are performing importance sampling on the joint space. So that's why we need Ln. There's no way around. Okay. There are various choices, and there are some default choices that exist, and some that have got some good properties that, in the sense that the importance weights have got a low variance. Okay. And this is well understood. And in those scenarios, the importance weight you see are of a very simple form. Basically, they just take into account the fact that you've got sample from mu n minus 1 and you want sample from mu n. So basically, you just correct with the ratio in order to take into account the discrepancy between the two distributions. So that's very nice. But one thing to remember is that for this type of scenarios, typically what you need is you need to assume that Mn, the mutation kernel, leaves mu n minus 1 invariant. So there are other versions of this story, okay, where basically you leave mu n invariant. But I'm going to focus on this scenario. And you see, and that's the important bit, is that basically within SMC, Monte Carlo methods, Markov chain Monte Carlo methods have been very important because of this property, that basically you want to leave a given distribution invariant, right? And you want something that is a general purpose algorithm. Okay, so that's SMC. And of course, this looks scary, but this is really simple. So here you run through the sequence of distributions, right? And here, basically, you just mutate the particles that you had from the previous iterations, you compute the importance weight, and there's a selection step, okay? But if you don't follow all the symbols here, that's not a problem, okay? Right, and more important is this picture, okay, which is wrong, by the way, but it illustrates what we want, because it's actually a particle filter, okay? But basically all the ideas are there. And you see here, this is the sequence of distributions we are going to track. So these, think of them as the mu n, and there's no clear purpose here, you know, there's no mu at the end of the day, but let's imagine that this is the case. What is important is what happens here, okay, because it summarizes what we do. And you see at time, let's say this is time 1 and this is time 2. At time 2, I've got my samples that basically are related to some of the samples at generation 1, okay? But you see that that it is believable that some of the samples do not have ancestors. They share the same ancestor, sorry, okay? So you see that here in particular, what's happened is that for the next iteration, basically we've sampled the next generation, so the Zn tildes, but there's been selection. So basically some of the ancestors disappear, right? Etc. So that's all you need to understand about sequential Monte Carlo methods. Is basically we try to sample from a distribution, we introduce some intermediate distribution, we approximate this numerically using a Monte Carlo methods. And really what is important is that at each iteration, we did typically a mutation kernel that leaves the distribution invariant. So we are going to rely on MCMC typically, and each particle gives rise to one mutated particle. Okay, and the latter is important because we are going to break the rule in a moment. Okay, so basically our contribution, integrator snippets. So first I'll go a bit through the link between, so most of the things I'm talking about are very simple, but there are many of those simple things that need to be put together for it to make sense. Okay, so the difficulty is not in the details, but in the big picture, basically. So now what I'm going to go over is how ODEs have traditionally been very important, explicitly or implicitly, in Monte Carlo methods. Okay, and one could even argue that most Monte Carlo algorithms rely on the discretization of ODEs, at least Markov chain Monte Carlo methods. Okay, so ODEs, we I think all know what this is all about, but here I'm going to consider a general ODE to start with, so something of this form with a field. And what is important is that we are going to consider discretizations, because very often we cannot solve this kind of ODEs, and we'll be interested in such scenarios, right? So for example, historically, one of the most important choices of ODE within Monte Carlo methods corresponds to Hamilton's equation. So what is the setup? So I'm interested now in sampling from pi of x, right? But in order to sample from pi of x, I'm going to make the problem apparently more complicated by sampling from a distribution defined on an extended state, right? So I want to sample from pi of x, but what I'm going to do is sample from a distribution defined on a joint space, where, of course, you can think of v as a velocity, right? So that's the idea. And here I'm going to assume that it is normally distributed. And basically the idea, so remember, we are defining a Monte Carlo algorithm. We've got samples and we want to mutate them in some way. And that's what you do in a MCMC algorithm. And that's what you want to do in a sequential Monte Carlo algorithm. So here, the idealized idea is that I would like to define an algorithm where if I've got samples from mu and hence from pi, which is what I'm really interested in, I'd like to define a deterministic transformation. So maybe for this community, I could call that normalizing flow. Okay, you define a normalizing flow, okay, a transformation, and you would like to define the transformation in such a way that the application of the transform to Z0 distributed according to mu is also distributed according to mu. That would be fantastic, right? So there is at least one flow that does this, is basically the solution of Hamilton's equation. And I'll write them down later on just to show you that they exist, basically, right? So if you take Hamilton's equation and you can solve them, basically they've got exactly these properties, okay? And one of the reasons is that basically if you solve the equation and, you know, go along the flow, basically you've got this property that basically the density doesn't change. There are actually other properties that turn out to be important practically, okay? And basically this has been sort of identified a long time ago in the Monte Carlo world, okay? So here are Hamilton's equation, just to show you that if you define mu in this way, and if you consider the pi of x of this form, then you can write a system of equation, provided that all the derivatives exist, etc., which is going to have this property and this property. Okay, of course, the problem in practice is that there are only very few cases where you can solve this analytically. Okay, so you've got to discretize and correct. Okay, so just a picture to show you how this looks like. So this is x, this is the velocity. And basically here, the target distribution pi of x was a univariate normal distribution. We've extended it with the velocity. So we are defining now a bivariate normal distribution. And what Hamilton's equations do, they follow the contour, okay? Because that's what I told you, that mu, basically the value of mu was left invariant by application of the flow solution of the ODE, right? So we follow the contour. And Monte Carlo algorithms that exploit these things, basically for random length of time, basically they follow the contour and then you resample the velocity. So you change contour and you follow the thing. So that's how these things work in an idealized world. But in practice, what you've got to do is that you've got to discretize. And basically by discretizing, basically you do not, in general, follow the contour. Okay, so that's the real world, and you've got to deal with that. Okay, and the way one deals with that is that basically in a metropolis hasting algorithm, well, you introduce an accept-reject step, which is going to determine whether your approximation is good or not somehow. And in SMC framework, basically you're going to use importance sampling. And actually, the two ideas are very much related, right? Oh, and by the way, why do we use HMC? So the belief is that basically, because you hope that this is not going to be too far, your acceptance ratio is going to be close to 1. And basically, there is the hope that in the X space, you're going to move far away from the point you've started from. So you're going to explore the space very quickly. And I'll show you some pictures that make you wonder if that's really how things are. Okay, so just to repeat, just to make sure that's a thing. So Hamilton's equations, that would be the ideal scenario, but we are going to discretize, and you don't need to remember this equation. What is important is just to remember the notation that psi is going to correspond to the discretization of these ODEs, okay? And we choose the discretization in a specific way for many reasons, but that I'm not going to detail here, okay? So here again, we do not have the property that the real system had, so we don't have equality. But what we know is that we've got properties like this, that if the step size is small, basically your error is going to be very small. So that's a good property. So you follow the contours, right? So your acceptance ratio is going to be good. So you get many good properties. And I won't stress on the second property, which is just which is primarily of a practical interest. That is, you don't have to compute a Jacobian. Okay, so if I put this together in a so-called hybrid Monte Carlo algorithm, so that is a metropolis hasting algorithm that uses the dynamics of the Hamilton's dynamic or the discretized Hamilton dynamic, this is what the algorithm is going to look like. So at iteration I-1, you've reached this point in the joint space. You sample a new velocity. So think of the picture. It means that you're changing contour, basically. And then you compute, you apply your integrator capital T times, and you've got to choose that capital T times to the state that you've constructed by concatenating basically xi-1 and your new velocity. You compute an acceptance ratio which takes into account or corrects for the fact that you're not using Hamilton's equation, the exact solution, and you accept basically psi to the power t of z as the next state of your Markov chain with this probability, or you stay where you were, right? So that's a standard HMC algorithm, and that's basically what is in Stan, okay? If you've heard about Stan, that's basically the what is behind Stan, or a more sophisticated version of this. Okay, so now I'm going to discuss what the issue is with this kind of approach. And maybe you already see it here in an MCMC. Basically, you see that we are wasting quite a lot of computation because typically you want T to be sufficiently large, whatever sufficiently large means, because you want to go far in the space. Okay, you don't want to make small jumps. So typically you want T large, but you see what happens here is that because you want to integrate, so you've got to compute all the states from Z to psi to the power T, right? But in the end, at best, you're going to use the endpoint of your trajectory. Okay, so that's quite a bit of waste. And of course, we were not the first to notice this, and some people have tried to use the other states, but in a different way and in MCMC, whereas we do it in SMC. And in fact, what we are suggesting would also affect the dynamics of the algorithm, whereas other techniques, they are just a post-processing step. Right. So now back to SMC. So I told you in SMC, we need an MCMC kernel if we want to get nice acceptance weights that have got little variability, right? That's basically the story. So what about using our HMC kernel? So here, our HMC kernel is a bit different from the algorithm I presented earlier because I do not refresh the velocity. Okay, so I tell you, I give you the pair XV, and you're going to just apply psi t, and there's an acceptance ratio, which is of the same form as before. And now I reiterate what I was saying earlier, is that you see that I'm going to mutate my particle. I obtain a Z prime, which is basically the result of the application of my integrator T time, but I've done all these computations in between, right? And I'm not taking them into account, right? In addition, it's really a pity. That's the not to use this information, because if you look back at what the integrator uses, basically it uses the gradient of the energy. And usually this is what is expensive, right? And if you push things in even further, so that's more of a practical remark than a mathematical statement, but very often, many of the costly quantities that are needed to compute the gradient of U, they are common to the energy itself, okay? So this is a toy example, but there are other examples. If you consider the case of a normal, basically you see that if I give you this, basically you're left with multiplying two vectors to get the energy, okay, which is much cheaper than starting from scratch. And basically what standard algorithms do, they just throw everything away, right? And why is that a pity? Because if I want to use importance sampling type ideas, basically this is exactly what I need. I need the energy to compute mu n minus 1, right? Okay, so before moving to the basically the snippets, so now we've got a bit all the ingredients to think. I just want to show you one picture to point out that everything I've said actually could be useful in very different scenarios. So imagine that your target distribution. So don't worry about these Gaussians here, okay? But just focus on the banana-shaped distribution, okay? And let's say you want to sample from this algorithm using a local algorithm with local update. So you see that the target has a very specific geometric properties, basically. And if you use a standard algorithm that basically updates your particles in a straight line, this is unlikely to work very well. You know, really what you would like to do is something that follows the contour or something like that. And there are many scenarios where you can actually describe those contours. So you can always describe the contours with an ODE, provided that you're differentiable, but in many scenarios, such as this toy example, you can very easily design algorithms that are going to follow the shape of the target distribution, therefore resulting in efficient algorithm. Okay, but I'll focus on HMC, which is just a particular case because it's the most popular application of ODEs in MCMC, right? So I'll skip these examples and I'll move on to our algorithm and show you how it works. Okay, so we've got a picture, okay, which sort of tells you the whole story. So there's one, so this is the second slide to remember if you were lost elsewhere. So the first slide and this slide. So how does it work? So again, SMC at iteration n-1, you had 5 particles. So of course, in practice, you use more particles than 5. And you remember what I was saying in standard algorithms, what you do is that each of these particles will mutate, okay? But we'll have typically only one mutation, okay? So there are versions where you've got parallel mutations, but what we're doing is very different. And here, what we do is that starting from each particle, we are going to start an integrator, okay? So think of these black dots as being basically psi to the power 1 of z, psi to the power 2 of z, etc. So basically, we follow the integrator, okay? So standard algorithms would only consider the endpoints, right? So here, what we do is that we consider all the points, and basically, instead of getting only the endpoints to compete, okay, for survival to the next iteration and give rise to the seed particles at iteration n, basically everybody here, including these seed particles, are put in the same bag, okay, and they are going to compete, right? So we use all the samples, and basically there's a big competition. Instead of being between 5, it's going to be between 5 times the number of integration on each snippet. Okay, and by the way, you see already on this that it is likely that you're going to cover the space much better than if you just consider the endpoint, right? So you see here in terms of the competition, for example, this particle had this integrator snippet here, and basically it gives rise to 2 seed particles. Okay, whereas this one, basically, well, no one was interesting and no one survived, right? Okay, so something a bit more concrete, right? So we are in the scenario where pi is a bivariate normal distribution and the kinetic part is a Gaussian, as usual. So this is our bivariate distribution, yeah?
Sorry, can you explain again on the last slide?
Yeah.
You now treat all of them as individual particles and
exactly
on the full thing, or is each thing's
no. As a you put all of them in a bag, okay, and they've got their own weight, which depends on where they are, right? And you're going to resample and select in that way, okay? Okay, so concretely what it means, so these are my seed particles. There are 5 of them. These are the contours of your target distribution in the X space, okay? So we ignore the velocity in this. This is just a projection in the X space. And you see that from each particle here, we start an integrator snippet, okay? So that's HMC in the X space. And by the way, you see here that I've always been puzzled by HMC, but you see that, so let's take this one. So you go through a region of high probability, right? And then you end up in a region of low probability, and this is the sample you're going to use, right? It's a bit strange, no? Right, anyway, and then what we do is that once you've created all those samples, basically you're going to select 5 out of all the dots here, okay? And these are your new seed particles for the next generation, right? And of course, you've ignored samples that were here, here, or here, right? Okay, so that's really basically the idea of what we are doing. And you see the difference with standard HMC is that basically we try to use all the points we've computed in the space. okay? And this is what the algorithm looks like. So of course, this looks like the sort of thing you shouldn't show in a talk, but I want to show you just one bit, okay? One bit, which is basically the weight that you're going to assign to each of those samples. So you see here, I've got the I correspond to the, if you like, the parent seed particle, okay? K is basically where you are on the integrator for that particle, okay? So that's your snippet index, right? And you consider this ratio between mu n minus 1 and mu n. So you can rewrite things in this way. So you see that here you've got a way that takes into account the fact that you're changing distribution, okay? You're going from samples that were distributed according to mu n minus 1 to samples distributed according to mu n. And here, basically, you take into account the perturbation. Okay, so now you're trying to target mu n directly, and you're taking into account the perturbation introduced by the integrator along the snippet. Okay, and basically, these are the weights that are going to be used for the selection among the n times capital T plus 1 particles. That's the idea. Okay. So high-level justification. So that's more for the specialists, but there's something, yeah.
So maybe I missed something, but how do you compute the density of because the dynamics you're using are not leaving the target invariant, right?
No,
Discrete.
absolutely.
Density of that.
Yeah, so that's why there's a bit of a mystery for a specialist here. But as you said, so first we change distribution. So I think you will agree with this. That's more or less traditional. But basically, if you look at this, this looks like very much like a Metropolis Hastings acceptance ratio. Okay, so here you're taking effectively into account the fact that the transformation does not leave mu n invariant. Okay, so you've got to do something, and the way to correct is the same. You do it in the same way as you do in the Metropolis Hastings algorithm. You compute this ratio that takes into account the fact that basically this is basically just a transformation of this sample. Okay, so you don't need to, at least if you look at the algorithm in this way, you don't need to think about, do I leave invariant or not? Okay, well, that's a very good question. So high-level justification. So
is Cn the one that leaves mu n minus 1 or mu n?
it doesn't leave, basically, it can be anything. So that's what I will say earlier. This is the amazing thing, is that here, basically, it's meant to be the integrator that is going to use the energy that corresponds to mu n or pi n.
Yeah, so mu n.
Yeah. So that's the thing. But in reality, you don't need that to be the case. Of course, it's going to work better if you use information about what you're trying to sample from. But in fact, in everything that I've said, the only thing I've used is that the transformations are invertible and they've got a Jacobian of 1. Okay, that's the only thing I've used. Right. Yeah. So here the Jacobian.
So you have Hamiltonian dynamics with some sort of Hamiltonian dynamics with the Jacobian.
Yeah. So which is the case when you use the right integrators. Okay, so I sort of skimmed on that earlier, but you'll show that then there are obvious generalizations. Okay, so this is the interesting bit, in particular for specialists. Okay, that basically this sort of looks like an SMC, but it's not our usual SMC where, you know, we know exactly that we've got one mutation and we compute our importance weight, but in fact it is. Okay, it's just that the target distribution is not, or the target distributions are not who you think they are. Okay, and basically this is the story. So I'll spend a bit of time on this. There's a bit of notation, but it's not, it's scarier than it is difficult. Okay, so the point is that, so you remember I was saying, I'm interested in sampling from the sequence of mu n's, and I've developed these algorithms. And what I'm going to say is that, in fact, what we are doing is that we are sampling from a sequence of distribution mu bar n, okay, which can be obtained through the mu n's. Okay, and in fact, they are of this form. So this is a standard SMC algorithm that targets this sequence of distribution mu bar n, which in fact are just mixtures of transforms of the mu n. So I need to explain a bit what this is, but that's very easy. So this is the distribution, okay, that you obtain if you sample Z from mu n, from the distribution you're actually interested in. You plug it into the integrator with a minus k that it turns out to be important. This is the distribution for this quantity. Okay, so basically, in other words, what this is some kind of probability distribution on what we call the snippet. Okay, and basically the key message here is that although you're interested in sampling Z, in fact, what you end up doing is you end up sampling the snippets. Okay, they become the state of your problem. Okay, so you're sampling integrators. Basically, that's what we are doing. Okay, so one thing that is easy. Okay, now I'm going to talk about, hold on, I wanted to sample from UN, and now you're telling me that we are sampling from mu bar n. And what I'm going to spend a bit of time on now is basically showing you that, of course, because of the mixture structure, you can go from the mu n's to the mu bar n's and vice versa. Okay, and that's what we exploit. Okay, it turns out that someone else had exploited the idea a long time ago, as I will show. So the easy bit is that if I sample Z from mu n, and if I sample K from a uniform, discrete uniform between 0 and T, then basically psi n minus K of Z is distributed according to mu n bar. Okay, that's obvious. That's the definition of mu bar n. Okay, so basically if I've got samples from mu n, it's easy to go to get a sample from mu bar n. Okay, you just sample from the uniform, apply the transformation, right, and you're in business. Okay, so that I'll skip. So now the bit that is maybe a bit more delicate, and that's the bit we are interested in, because I'm telling you we are going to sample from the mu bar n, okay, but I'm really interested in expectation with respect to mu n. So I've got to find a way of going back to it. So of course, for people who are familiar with mixture, that's easy. Okay, if you can sample from the label distributions conditional upon the state, then you're in business. Okay, and that's what I'm going to talk about. So now we are going to assume that we've got a sample from mu bar. How can I get a sample from mu n? And basically using the mixture property, if Z is distributed according to mu bar n, if I sample K from the conditional distribution, okay, which is defined here, which is this times this, right, obtained from the joint model underpinning this sum, okay, if you sample the label, then you've got this property, obviously, and at least intuitively, you've got that basically this, and the power is really a positive power, okay, you're distributed according to mu n. So what I'm trying to say here is that if you give me samples from this distribution, and if you can compute this conditional distribution, which are discrete, right? So there's a good chance that you can do it. Basically, if you can sample this label, then you just take your Z, you apply this transformation, and you obtain a sample from mu n. Okay, so what I'm trying to say again here is that if I can sample from this distribution, then I can compute expectations with respect to mu n, right? Okay, so what this relies on is simply the change of variable formula, okay, which basically tells us that, yeah, if I got a sample from mu, so here I got rid of the n, if I compute Z from as a, by applying this transformation to Z node, then I get a sample from, by definition, of the push forward. Okay. But then if I look at psi n of K of Z, of course, I obtain Z node. So you see here, I'm knitting, deknitting the same thing. So it looks really, really silly, but it turns out to be very useful. So overall, what this means is that the expectation you're interested in, you can rewrite it in a complicated way like this. You just say it's the push forward of Z0 by this transformation. But then when you use your sample, you apply the inverse transformation. So it looks like you haven't done anything, right? But along the snippet, this turns out to be important because you will have sample from mu bar. Okay, so if you do a bit of calculations, and I speed not, an expectation of a function with respect to f, basically, you can always write it as an expectation of samples according to mu bar n. And here you use the conditional distributions of the labels in your mixture model, and you apply them to psi nk of z, right? So you see that this tells me if I sample from this, then I can use all the samples along my snippet to compute the expectation I was actually interested in, right? Okay, so basically the conclusion at the time of slide 26 is that basically this is just an SMC algorithm, okay, that can exploit all the states that you're creating along any integrator you're interested in, and you can compute expectation very simply, practically. Okay, and just to show you that this is this can be computed in practice. So in most scenarios, the conditional distribution of your labels are exactly of this form. Okay, so that's something you can compute, and this is what the estimator is going to look like. Okay, so you just put everything together and you get samples. You get an estimator of with respect to the distribution you were interested in. Okay. The other advantage of identifying this kind of algorithm as just an SMC algorithm is that you can reuse every result that exists in the literature. Okay, so you don't have to work too much. What was difficult was to make the bridge between the two ideas. So I'll skip this. So that's for the specialists. The kernel in the mu bar space is a bit complicated. I will skip that, but it does the sort of things you expect. And here, the only thing that is important is that, so again, it's the familiar kind of thing, scary and whatever. What is important is the importance weight. And you see there's something interesting, I think, in the importance weight, is that you see that when you perform selection, okay, what you take into account is implicitly, you see in mu bar, you take into account the snippet in the, if you like, n+1 space. Okay, you're not comparing with particles. You're saying, I'm selecting you because you and all the states that you generate with your integrator, overall, you're interested. Okay, and this is, I think, what makes the whole thing work very well in practice, is that we get that robustness that instead of basing our decision on just one point, we base our decision on the whole trajectory. Okay. And if you think of the pictures I showed you earlier, indeed, that makes sense. Okay, because we had trajectories that started in the wrong place, ended in a bad place, but in the middle, we were crossing a region of high probability, or density, sorry. Okay, so I'll skip these things, you know, that explain one to two things are equivalent. How much time have I got?
How much?
25, but that's with the extra.
Yeah, we can. So if you do 20 minutes,
Okay, so maybe what I'll do is that I'll, because it could be a bit too, yeah.
I have one question. So the plot you showed on HMC, where you said it's quite weird that you select the point that is not in the correct region.
Or you try to, yeah.
Yeah, but don't you have the same problem here? Because then, since you have a volume preserving transformation, when you're looking at the weights of the density of your sample in the snippet, you're basically only looking at the density of the initial sample. of the starting point, because
no. Because you look basically at the average, if you like, at the average of the metropolis Hastings rates, acceptance ratios along the way. Yeah, I can, you know, it's here, right? You see here in this guys, you've got the average of the HMC acceptance ratio at each step of your integrator, and you're taking the average. Okay, so you're not, but that's a very important point that is not obvious at first sight. Is that basically you base your decision, you're really sampling the snippets, not the states. Right? So it's basically you're basing your the decision on what your snippet has covered, basically, not where you've ended up or where you started from. Okay. So I'll skip this. So that's the, someone had a similar idea. Most of you were not born, maybe, a long time ago in the context of MCMC. Okay, but I'll skip that. I think I'll move to the the obvious generalizations. So that's actually an important point. Is that basically, and I've hinted at that already. Here I've considered integrators because they are popular, but basically I could have considered transformations in general. Okay, and the only property I've really used here. So I've used the fact that basically my transformation arose from an approximation of something that was interesting, you know, the HMC or following contours and things like that. But basically, they could be any transformations. And the other thing that I've used is that the fact that basically the transformations were volume preserving, right? But that's it. So if you got a family of invertible transformations or normalizing flows, basically you can use your normalizing flows in this context. But of course, in general, if you've got a Jacobian, you will have to compute the Jacobian if it's not known to be one. Okay, but that's an obvious transformation. And of course, you can change the weights, but that's just really not so important. So I'll jump to these applications. So hopefully that will sort of work. So we've considered, so I'm going to destroy. So there are some links with other things in the literature, but I'm not going to dwell too much on this here. I'm going to show you an example. So here we are considering an example that is not the most challenging problem in the world, but it's been used elsewhere, and we had to start somewhere, to be honest. So logistic regression, so we're on a Bayesian framework. There is a likelihood, there's a prior, and the form of which is not that important here. What is important is that the distribution we are interested in sampling from is of this form. Okay, pi of x is proportional to a likelihood times a prior. And we are going to use SMC in the following way. So basically, we take into account the likelihood function progressively. Okay, so the lambdas here are going to be 0 to start with. So we start from the prior and we incorporate the likelihood progressively because we believe that this is the bit that is going to make the geometry of the space complicated and hence difficult to sample from. Right, so we've got a comparison in the manuscript, but what I'm going to focus on here is the adaptivity that we can introduce. So that's not in the technical report, but is going to be in the update that is about to come out. So here, this is just a picture to show you what information you can get from using SMC, basically. And that turns out to be very important in the context of when you're using HMC. So just a bit of recap. You remember we are discretizing Hamilton's equation. So there's a step size, there's a number of steps, and basically there is that idea of effective integration time. So that's if you were to integrate, if Hamilton's equations were really tractable, you would integrate numerically, and this is the corresponding time horizon that you would consider. And here, for various values of the parameter, I'm showing you some statistics that arise from the particles at a given iteration of the algorithm. So for those of you who are familiar with knots, okay, basically this corresponds to basically a probability that is these are the statistics of where knots, the knots criterion is triggered. So what is knots is basically, you remember those trajectories of HMC, and they tend to, some of them were coming back towards the initial point. So what knots tries to do is to say, okay, you integrate, but as soon as you detect that you're heading back towards your starting point, you stop, right? So here, of course, we are integrating with a very large number of integration steps. But what we did is that for that population of particles, we detected when basically folding back of the trajectory was occurring. And you see, that's quite striking, okay, that you get that information, okay? And what is important here is that by just looking at it, what you can tell is that probably T was far too large, right? Because all this is wasted, because it means that you're probably going back towards the initial point, okay, along these iterations, right? And here we've got the effective sample size, which is a measure of quality of your samples as we increase the number of integration steps. And you see that by increasing T here, there is a gain, but then this flattens out. So again, we get some indication that T was too large. So basically all these computations are probably wasted here, okay? And the same here. So basically what we've tried to do in particular with Mauro is to try to exploit all that information that is in our SMC in order to tune these parameters here. So I'm not going to detail how we did it because I would need another hour, but I'm going to show you to give you a sense of how robust the algorithms can be. Okay. So here is a preview. So of course, we've got also to adapt basically the sequence of lambdas. You remember that those lambdas, they determine the sequence of mu n, and we can learn that sequence on the fly as well and determine them. And here, so what was the game? Here we considered, or Mauro considered, 3 initial discretization step sizes. And by hand, it was determined that a good step size was 0.1. Okay, so that's basically the graduate descent algorithm gave us 0.1. And then we came up with an algorithm where we start with values where basically epsilon was too small and epsilon was too large. Okay, and here is the adaptation. So here we've got the sequence of lambda that goes from 0 to 1 in all cases. So that's not the bit that is interesting. What is interesting is this, is that here you see we start with a very small epsilon, which means that we don't go very far in the space, by the way, okay? And you see that the algorithm detects that this is too small and increases it and goes towards a value that is almost 0.1, okay? Here we started with a good value and we just change it only a little bit. And here basically epsilon was too large, and that's over several realizations, by the way. And basically the algorithm recovers the near 0.1 good value, okay? And as Mauro says, so we've come up with various strategies, but whatever you do, it seems to work, okay? At least for this, example. So this is for the specialist, the effective sample size. So it's very poor when you start with a bad epsilon, but you see that you recover very quickly. So this is again the evolution of the values of epsilon. So this is what happens if you don't adapt, right? So you start with these values, but you keep them fixed. So that's again the evolution of the tempering parameter, but this is the ESS. So here you're not doing too bad, but of course we don't have any information about the geometry of the set of particles. So they are not covering the space very well. So you see that here this collapses and recovers. So it looks like you're doing something good, but if you look at the number of unique particles, basically you see that it crashes. Okay, so basically the SS is not a perfect measure of performance. That's the conclusion. So now, estimation of the normalizing constant. So that's a big problem in Bayesian statistics. And here the idea was for the 3 step sizes, so good and bad for 2 different reasons. Mauro compared basically the statistics. So basically I can't remember the number of runs, to be honest. I think it's 10 or 20, and we've got box plots where we estimate the log normalize, the logarithm of the normalizing constant for the Bayesian model considered earlier. So fixed means that there's no adaptation. This is the adaptive bit. And you see that basically the adaptive bit always recovers the well-tuned algorithm. And this is just, so this was put on the same scale, and these are just zoom-ins of the thing, right? And Mauro went all the way. So he tried, so that is the same thing for 2 adaptive algorithms, starting with a step size of 10 minus 3, 2. So he went to, what is it? 10. Okay. And you see that the results are very stable over a very long period. And in fact, what he told me this morning is that here, in fact, if you look at the epsilons, you get the correct value. But the initial estimates for the normalizing constant are so bad that basically they affect what happens towards the end of the algorithm. Okay, that's just without the lab. And I'm going to stop here.
Yes, thank you for this hour-long talk. I think 70 minutes or so. It was the right choice to start earlier. So any questions?
So I did it overrun. Yeah.
Not technically because we started early, but yes.
I have a question about the asymptotic bias. So this is very nice. You can write it in the fragments. You see some about the theory. Can you get, but you get the normal, the asymptotic variance for your joint distribution, the mu bar. Can you recover the one from mu from there? And can you show if it's larger or bigger?
Okay, so we've got very little theory about this at the moment. But if you look at the appendix, we've got some results where we just look at the important sampling scenario. Okay, so we don't look at the SMC, as you know, that's quite complicated. And what you can show is that introducing the integrator helps you. That is, you reduce the variance, whether it's a lot or not. I don't know. My theory is that basically what matters is the support, is that you increase the size of the support. Initially, so we've got some attempts at developing a theory and whatever, but nothing really came out of this. But I don't believe that it's the variance per se that is helping you. I think it's really that instead of just considering points that are useless, you increase your chances of hitting the good region. So to answer your question precisely, we don't have anything concrete. There are some partial results that indicate that you don't do worse. Yeah.
Any other questions? I have a few, I guess. So first question, relate to program. Why ODEs and not diffusions? Because you have the canons in the case in the diffusions, right?
Yeah,
Would-
so first diffusion, it would be more like the work of Nicolas. And we haven't looked at that. No, we were interested in this because I got a personal interest in the basically the convergence of integrators and Monte Carlo methods. In fact, it's something that has been very little touched on, and I think it's quite interesting. So it was a question of taste and interest in something from manifolds and all those things.
The other question.
Then you need, if you use a diffusion, then you would have to compute the density also.
Yeah, but because of the reversibility, there are many things you can compute in that case.
Yes, but then you will discretize the diffusion. Then you need
Absolutely. You've got to
not be exact in that case.
Yeah. But I was thinking of your question as why didn't you use MCMCs?
Something like that.
Yeah. Or doing that, and that's basically more like Nicolas' work.
The other question I had with I mean, ESS was getting better with the, I don't know if I interpreted correctly, with the integrator.
Yeah.
But intuitively, I thought maybe it would get worse because you would have basically, normalizing the weights would get more problematic as you have more samples. Or...
Yeah, it didn't in this case. I don't know. I don't know why.
I mean,
there are many things we don't understand.
Mm-hmm. All right. Any questions? Not, then let's thank the speaker again.